Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go with another video here on Basic Periodic Trends worksheet. All right, so we have already finished the first worksheet, and that was Basics of the Periodic Table. You should probably watch that first. The other video that you should watch is actually the lecture series for this particular unit here on periodic trends for general chemistry. You should see it all in my playlist. All right, so without further ado, let's get moving on this worksheet here. And you're probably going to need a periodic table at hand, and that would be very important. So let's get moving here and get some problems done for this periodic trends basics worksheet. Here we go. Number one, how is the modern periodic table organized? Atomic number. Okay, by the way, Dmitry Mendeleev organized his periodic table according to atomic mass, and currently our periodic table is organized according to atomic number. Okay, there are some slight flips of elements when that occurs, but really and truly, it's really, really important that we understand that the periodic table is organized according to atomic number. And in fact, I'm going to show you exactly what I mean by that. Okay, so I'm going to pull out the periodic table of which I use in this class for general chemistry. Okay, and here we go. Here is the periodic table that we use for this class. Okay, it's a wonderful periodic table. And so here we go. It is a thing of beauty, as I have mentioned in my previous video. It is truly a thing of beauty. And that is the periodic table is a thing of beauty. I love it. So highly organized. So here we go. The modern periodic table is organized according to atomic number. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And I think you guys get the point. Even these elements 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, etc. It's still organized according to atomic number. Okay. So like I had said before, Dmitry Mendeleev organized his periodic table according to atomic mass, and that was slightly different. There are a few elements of which have flipped positions, okay? So for example, we'll just take a look at cobalt here, cobalt and nickel, okay? So you should see that cobalt has a mass of 58.93 and nickel has a mass of 58.60. So technically, according to, and I'll zoom in on this section of the periodic table so you can clearly see that. Okay, this is just one example of a few on the periodic table in which the mass would commonly increase. So you should see that the mass generally increases. So 47.87, 50.94, 52, 54.94, 55.85, and then we have this anomaly of the mass actually decreasing for cobalt and nickel. That's just one example of where Dmitry Mendeleev would have flipped cobalt and nickel in regards to their placement on the periodic table. And that's why our modern periodic table is organized according to the atomic number. And the atomic number, which is highlighted in yellow on this periodic table, so the atomic number highlighted in yellow on this periodic table is, let's see, I will go with the key here, atomic number. That is that top number right there. The periodic table is organized according to atomic number. Atomic number is actually equal to the number of protons. So the atomic number is equal to the number of protons. And that is symbolized as a P with a superscript. And I'll just zoom in on that section right there as well. So the atomic number, that's the number highlighted in yellow. It's equal to the number of protons. It's a very critical, important concept here of the periodic table. All right, fantastic. So we've got that nailed. Let's go on to our worksheet again and continue on answering these problems here. So here we go. Number 2, groups are horizontal or vertical and periods are horizontal or vertical. So let's take a look at our periodic table again and figure out what are the groups and what are the periods on the periodic table. All right, so we're going to move our periodic table back over here, zoom on out so we can see the entirety of our periodic table. All right, and so what we're going to do is label the groups and label the periods so that you have a full understanding of those. So this is a group, a group, a group, and a group. And then periods are here. Period, period, excuse me, period, period. So that means that the periods on the periodic table are these horizontal sections of the periodic table. And there are 7 periods to our modern periodic table. Those are periods. Groups on the periodic table are vertical columns. Groups are vertical columns. These are groups. There are a total of 18 groups on the periodic table. Vertical columns are groups. Groups are vertical columns, and periods. Periods are the horizontal sections on the periodic table. Okay, hopefully that's not so bad. So let's answer that question right here and put this down on our paper. Here we go. Zooming on in. And let's see, groups are vertical, periods are horizontal sections on our periodic table. Awesome. Hopefully you got that nailed down. That's pretty easy here. So now that we have that nailed, let's just come back to our periodic table again and talk about those groups and periods. So these groups are vertical columns, and the reason why the elements are organized into these vertical columns on the periodic table and are called groups, another name for this is a family. And typically, if you're in a family, then you have common similar things within other partners or elements within your family. And so a group and a family have a lot of similarities. That's why it's called a group or a family. And that is, for example, if you look at group 1 or group 2 or group 3, 4, 5, 6, 7, and 8 in the old school method, those groups have the same number of valence electrons. So each column on the periodic table, each group, each family on the periodic table has similar number of valence electrons. Whereas the periods, the horizontal sections on the periodic table, they do not have nearly as many similarities as what the groups have on the periodic table. Okay, so periods increase by 1 atomic number at a time horizontally, and groups increase or decrease by large factors of atomic number dramatically. Okay, and there are going to be lots of trends of which we're going to understand based on the location of the element on the periodic table. So the periodic table is organized according to location, 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 and location. Those are the 4 quantum numbers, and that's the essential. All right, so let's move on now that we got groups and a family. That's in a column, vertical column on the periodic table, and the periods, the horizontal sections on the periodic table. We got that nailed. So let's move on to the next question here. And so let's zoom in on here. All right, so our next question is the following. It says, number 3, does the atomic radius increase or decrease as one moves down a group? So what we first need to do is draw the general trend for atomic radius. So what we're going to need is another periodic table. That's right. We are going to be burning through periodic tables like it's no tomorrow here today. So Don't worry. I'm going to be writing up all kinds of periodic tables. So we need to be talking about atomic size or radius. So we're going to zoom on out. We're going to take a look at this periodic table here, and we're going to be talking about atomic size and radius. Okay. All right. So you got your beautiful periodic table. You're quite happy with this lovely periodic table here. And you got all the elements on there, and we need to figure out the size, atomic radius or size. So let's write that down. So atomic radius or atomic size. So if you imagine an atom, it is a sphere. Okay, and so this is my rough representation of a sphere. And if you had a sphere, then the radius would be from the center of that sphere to just the outer distance of that sphere. That would be the radius. So this line right here would be the radius. So all atoms are compared to their radius. All right, fantastic. So now we understand the concept of radius, hopefully, and that is 1/2 that distance of that sphere. So now we need to look at the size in terms of radius and what happens. So in terms of radius, this is what happens. So radius, as we go down a group or family, is going to increase going down a group. And there are many reasons as to why that is the case. So you really need to be looking at my honors chemistry or advanced placement chemistry videos to figure that one out. It's beyond the scope of this course for the moment in time. Okay. But then the radius, so this is a increase as we go down a group. So I'll write that down here, increase. So that's an increase in radius as you go down a group. And then there is, as we move across a period to the right, there is a decrease in size. Okay. Now, all textbooks give these two answers here, and that is an increase as you go down a group and a decrease as you go to the right within a period. But I'm going to make one slight modification here, and that is it will make it easier if we put the arrows together. And if we put these blue arrows together, you should see that this blue arrow with the period is going from the right to the left. This would be an increase if the one going to the red arrow going to the right is a decrease. So this is an increase. All textbooks will tell you the blue and the red arrow of increasing going down a group and decreasing across a period, and that is most certainly correct. So the question is for this next question here. And so let's zoom in and go back to our worksheet here. And it says, does atomic radius size increase or decrease as one moves down a group? Well, as you move down a group, it increases. So increase. Perfect. All right, so that should be our answer there. And then the next one, the next question here is number 4. Does the atomic radius or increase or decrease as one moves to the right within a period? So as you move to the right within a period, it decreases. Okay, so hopefully you got those ones nailed. So that's 3 and 4 that we just did in relationship to size of the elements on the periodic table, and that is seen in this right here periodic table. Fantastic. We're going to come back to this periodic table to answer some questions, but let's move that off to the side so that we can answer some other questions. Okay, so then the next question here, number 5 and number 6, they go together. And so 5 and 6, they go together. And let's see if we can nail this down. All right. says, does electron affinity, EA, increase or decrease as one moves down a group? And does electron affinity, EA, increase or decrease as one moves to the right within a period? Okay, so let's talk about the trend for electron affinity. So we need to figure out what is electron affinity. And so here we go. Electron affinity. Um, So what is electron affinity? Electron affinity is whether or not that element likes electrons. So do you like electrons or do you not like electrons? That's really the question here for electron affinity. And so here is the trend for electron affinity. So electron affinity, as you move to the right, increases, and as you move up in a group, increases. So overall, electron affinity is increasing in this direction. So let's write all that down so that you've got those. So electron affinity increases and increases. So as you move to the right within a group, electron affinity increases. As you move up a group, electron affinity increases. So let's now go back to our question here and see if we can answer that. So does electron affinity increase or decrease as one moves down a group? It actually decreases as you go down a group because it increases as you go up. Does electron affinity increase or decrease as one moves to the right? So it increases as you move to the right within a period. All right, fantastic. And we can write these words here: decrease and increase. Perfect. Now we've got those. All right, so let's tackle the next problem here, and that is electronegativity for question number 7 and 8. Does electronegativity increase or decrease as one moves down a group? Does electronegativity increase or decrease as one moves to the right within a period? So we're going to get out a new periodic table again, and electronegativity. So here we go, electronegativity. Let's cover that one. Let's get a new color pen here. Excellent. Electronegativity. Okay, so electronegativity. So it symbolizes a scripted X here. So electronegativity, it increases as one moves up a group and increases as one moves to the right within a period. So overall, the net increase is right there. Okay, so let's write those down. So this is going to be an increase going to the right within a period, and an increase going up the group. In fact, the values of electronegativity, which are going to be important in the future, would be the following. Okay, this fluorine is 4.0. It's like the highest GPA. I'll zoom in on this section here. So fluorine is 4.0, oxygen is 3.5. Nitrogen is 3.0, as well as chlorine is 3.0. Carbon is 2.5, as well as sulfur is 2.5. Boron is 2.0. You should see that this is just like GPAs on a non-weighted scale. Of the highest GPA of 4, that's an A, then a B plus as a 3.5, a B as a 3.0, and then a C plus as a 2.5, and then a C. And then there's one other element that's really important, and that's hydrogen, which has a value of 2.1. It really doesn't fit within that column there. Cesium down below here is between like 0.7. So you should see that that is the value for that. Okay, so let's just zoom on out here and let's look at this here again, and let's answer the question here. So Electronegativity increases as you move up a group and increases as you move to the right within a period. So let's see what the questions were. And let's answer those. So number 7 and 8, does electronegativity increase or decrease as one moves down a group? So as you move down a group, it decreases. Does electronegativity increase or decrease as one moves to the right within a period? And it increases as you move to the right. So let's write these down. Decrease and increase. All right, perfect. Those look good. All right. All right, so now we got electronegativity nailed down. So let's go and look at our next one, and that is number 9 and 10. Does ionization energy increase or decrease as one moves down a group? And does ionization energy increase or decrease as one moves to the right within a period? So we need to get a new periodic table. Oh my, we're going to have a bunch of periodic tables here labeled up, and this is going to be ionization energy. So let's see if we can get up into this. So zooming on out, we've got our full-blown periodic table right here. And so ionization energy. What is ionization energy? It is the removal of an electron from the gaseous state. That's right. So it is the removal of an electron from the gaseous state. All right. So, well, again, if you want more information on that, you really need to be watching my honors chemistry or AP chemistry videos. So let's take a look at what happens here. So ionization energy increases as you move up a group, and it increases as you move to the right within a period, and that is the overall ionization energy increases moving up and to the right. So let's write that down here. So this is an increase, and this is an increase. And that is, you're just following the arrows, in other words, okay? All right, so let's answer questions, of which it says here on the worksheet. And let's see if we can get this on here. Does ionization energy increase or decrease as one moves down a group? So as you move down a group, it decreases. And does ionization energy increase or decrease as one moves to the right? That would be increase. So let's write those down. Decrease. Increase. All right, so I'm going to give you just a little overall summary so that you have all this. I want you to understand something that's very, very important here. Okay, so let's move this off to the side. So what we have is the following. Atomic size, which is radius. Notice the trend. Going down a group, it increases. Moving to the right, it decreases. Okay, so moving down a group increases, and moving to the right is a decrease, right? Okay, then electron affinity, as one moves down a group, it decreases. This is exactly opposite of size. And does electron affinity going to the right, it increases. This is also opposite of size. Electronegativity decreases going down a group and increases going to the right within a period. Ionization energy decreases going as one moves down a group, and ionization energy increases as you move to the right within a period. You should see that I have highlighted the in yellow the size. In yellow the size is exactly opposite that of ionization energy, electronegativity, and ionization energy. In fact, electron affinity, electronegativity, and ionization energy follow the same trend. So let's take a look at that here on our periodic tables. And that is, there is ionization energy, That is the trend. Here is the trend of electronegativity. It's the same. Here is the trend for electron affinity. That is the same. And oh my, here is the trend for size, atomic size, and that is exactly opposite. All right. So that's a really good summary right there. So atomic radius or size increases going down a group and to the left within a period. So they're very big here and relatively small there. And you should see that electron affinity is exactly opposite. That arrow is going up and to the right. And electronegativity, that arrow is going up and to the right. And ionization energy, that arrow is going up and to the right. So ionization energy, electronegativity, and electron affinity all follow the same trend, although they are different things, they do follow the same trend. All right, so let's peel those away, and then we need to do the next periodic table here. Oh my, yes, I know. You love periodic tables as well as I do. And so let's nail this down here with a little bit of weight. So our next question here on our worksheet is to answer the following. It says, locate on the periodic table the alkaline metals, alkaline earth metals, transition metals, representative or main group elements, inner transition elements, the lanthanides, the actinides, the noble gases, the diatomics, and the halogens. That is a lot for us. So what we need to do is label up this periodic table. So I'm going to turn this off to the side so that we can label these here very nice and easily. So this first group right over here, and I'm going to highlight these sections so that you can see them, is the alkali metals. So the alkali metals are this group right here. That's the alkali metals. Okay, fantastic. The alkaline earth metals. The alkaline earth metals is the next group over, which is group 2. All right, so let me just zoom in on that so you can see that here. Here we go. So there we go. We have the alkali metals and the alkaline earth metals. Okay, that is group 1 and group 2. Why the name alkali? Alkali comes from the fact that when you put these metals in water, and I'll flip this over here like this. When you put these metals, either group 1 or group 2, in water, what do you get? You get a basic solution, and a basic solution is an alkali solution. So that's why those are called that way. All right, another one that we're going to label are the transition elements, So let's write that down. So I'm going to flip this periodic table, and the transition elements are this grouping right here. Okay. So these are the transition elements right here, and I'll write this down. So these are the transition elements. This is known as the D block. And we have already talked about the S, the P, and the D type orbitals. So this is the D block of the transition elements are the D block. Okay, another group here are the inner transition elements, and we will label those as well. And that will be, notice that this line right here, these elements fit in that line right there. And so these are the inner transition elements, inner transition metals. They're all metals, so you call them any inner transition metals. So I'll call this inner transition elements. That's also known as the F block, right? They are F-type orbitals, right? Then that nails down another one. Now we have another one, and that is the lanthanides and the actinides. Well, here's lanthanum and here is actinium. And so this horizontal section right over here are the lanthanides. That goes here. And then this horizontal section right here are the actinides. Right here like that, okay? So we got the lanthanides and we got the actinides. Now we need to label the noble gases. And that would be, I'm going to tilt this here like this. And the noble gases, let's see what we can do here. We will go like this. These are the noble gases. All right. That is slammed far on the right-hand side of our periodic table are the noble gases. All right, now we need to label the diatomics would be next and the halogens. So let's do the halogens first. Okay, these are going to be the halogens. Halogens. Then we're going to do the diatomics. All right, folks, here we go. Diatomics. And we will label these in this green right here. And so here is our numbering. That's N2, O2, F2, Cl2, Br2, I2, and then one more, and that's going to be H2. So we're going to completely color these in as the diatomics. You should see that there is some overlap between diatomics and the halogens. And then we need to scroll our periodic table over here, over to hydrogen. So hydrogen is, by the way, not an alkali metal. So we kind of cross that out for the alkali metals, but it is a diatomic. All right, we have one more thing that we need to label, and that is the representative or the main group elements. And these are going to be the S and P blocks. So the S and P type orbitals. So this is what we're going to do. And so let's zoom on out just a little bit so you can see all of this entirely, completely. Okay, so a little bit of funny here. What grade do you not want to get in a chemistry class? That's right, folks. You don't want to get an F. So what we're going to do is we are going to fold out the Fs. So we're going to get rid of the Fs. Why? Because we don't want to get an F in a chemistry class. So we're going to fold that out. All right. Perfect. What other grade do you not want to get into a chemistry class? That is a D. So what we need to do is we need to fold out the D block. So let's fold out the Ds. So effectively what we're doing is we're going to fold it such that we can see the Ds. And from there, so there are the Ds right there. What we're going to do is now we're going to push the rest of it together, which we had before. And right here, this right here, what you see, S and P type orbitals. Notice that there's that break. If you remember from a previous video, there's that break. S and P type orbitals, these are the main group or the representative elements right there, S and P. So let's unfold this periodic table and then let's just do a quick little summary of everything so that you have it all. Okay, so first of all, we have group 1, which are called the alkaline metals excluding hydrogen. That's labeled in yellow. Then we have the alkaline earth metals, that's group 2. Then we have the transition elements or the transition metals. They are transitioning. These are highlighted in the green rectangular box. That's the D block. We have the inner transition elements, which actually fit within the transition elements. Within the inner transition elements, we have the lanthanides, and then we have the actinides in these horizontal sections. We have the noble gases far to the right. We have the halogens one group over from that. We have the diatomics in this L-shaped pattern right here, and notice their formula is di for 2. That's N2O2F2Cl2 Br2 I2 and H2. All right, and then we have the main group or representative elements, which are the groups 1 and 2 and all of the P's without the D's and the F's. If you fold those out, that would be the representative or the main group elements. All right, we've just labeled the entire periodic table according to their categories. Okay, we're going to peel this periodic table away. All right, we're going to come back to the questions at hand with our worksheet. We've answered many questions, but we are certainly not done. So we have labeled up our periodic table. So we have located all these groups and categories here on the periodic table. So now what we're going to do is we're going to answer some other questions. It says, which elements in each pair has the larger electron affinity? So what we're going to do is we're going to come back to all these periodic tables that we have labeled here. We have worked so hard. So we have electron affinity of sodium or lithium. So sodium or lithium. Okay, which one has the larger electron affinity? Well, you should see that electron affinity increases as you go up. So it would be most certainly lithium. So I'm going to circle that. By the way, I do have this in the generic, let's zoom on in here just a little bit. So this is A, X, and Z. So you should see that these are all labeled very nicely. The Z is right there such that you can find these elements rather quickly here. That's the whole point. Okay. All right. So let's do the next one here. And that is strontium and magnesium. That's element 38 and number 12. So number 38 and number 12. So number 38 and number 12. Which one has the larger electron affinity? Well, the one that's higher up, because that's what the trend says. As you go up, you get larger. So between these two, it would be magnesium. Okay. The next grouping that we are going to compare is sodium and aluminum. That's element 11 and 11 and 11 and 13. So here is 13, there's aluminum, and here's 11, that is sodium. So which one has the larger electron affinity? So electron affinity increases as you move to the right. So aluminum is further to the right within that same period. So it would be most certainly aluminum. Okay. Then we have cesium and lead. So let's highlight those. That is element 55 and 82. So let's find 55 and 82. Here is 55 for cesium, and here is 82 for lead. So they are also both in the same period. The one that is further to the right will have the larger electron affinity. Excellent. So that will be the lead. The next one here is going to be barium, element number 56, or fluorine, element number 9. So 56 or 9. So 56 barium and 9 fluorine way up over there. So let's zoom on out just a little bit so that we can see all this here. All right, so we got our full periodic table. So between barium and fluorine, which one is up and farther to the right? Fluorine by far. So that would be a larger electron affinity. So you should see that. Perfect. So let's just slap this right here, and you should see that we are comparing the ones that are circled or highlighted with the similar color. And you should see that as you move up, you get larger in electron affinity. As you move to the right, you increase in electron affinity. As you move up and to the right, you increase in electron affinity. Perfect. So we've got that labeled. That's number 12. Now we're going to do number 13. So let's zoom in on these questions here. It says number 13, which element in each pair has the larger electronegativity based on periodic trends? So we're going to pull out our periodic table on electronegativity, and let's follow these ones. So we have sodium number 11 or lithium number 3. So here's our periodic table on electronegativity, and we have lithium and sodium. And which one has the larger electronegativity? Well, the one that is higher up, that would be most certainly lithium, because as you go up a group, it increases. As you go to the right, it increases. So we're just comparing in the same group or a group or family. So as you go higher up, it will be higher electronegativity. That would be lithium. We'll do the next one here, and that is between strontium and magnesium. So strontium is element number 38, magnesium number 12. Let's find those on our periodic table. We have strontium, that's element 38, and magnesium number 12. Okay, so similar type of issue here, and that is the electronegativity increases as you go up. So it would be most certainly magnesium would have a higher electronegativity. So let's write that down. Magnesium has the higher electronegativity. All right, the next one is between sodium and aluminum. That's 11 and 13, atomic number 11 and atomic number 13. Okay, so which one has the higher electronegativity? Well, they're in the same period, and that is as you go to the right, they increase in electronegativity, and that would be aluminum would have greater electronegativity than sodium, so aluminum. All right, the next one is cesium, and that's element number 55 or lead number 82. So we have cesium or lead. So that would be cesium, element number 55, or lead number 82. Which one has the higher electronegativity? That is the one that is further to the right. That would be most certainly lead. So we're going to write that down here. Lead has a larger electronegativity. All right, then the final one of this grouping here is barium or fluorine. That's number 56 or number 9. So we're going to have barium or fluorine, and so that is barium or fluorine. Which one has the greater electronegativity? Well, barium is lower and more to the left, and fluorine is higher and more to the right. So fluorine will have the greatest electronegativity. In fact, fluorine is the largest in electronegativity of any of the elements on the periodic table. So we're going to label that as that one right there. Perfect. So now we've got all those answered. Okay, so now we've done our electron affinity, we've done our electronegativity. Now we're going to do our ionization energy here. All right, perfect. So says which element in each pair has the larger ionization energy based on periodic trends. So we have sodium or lithium again. Okay, and so we have sodium or lithium. We have, here's lithium, element number 3, or element number 11, sodium. Which one has the larger ionization energy? So ionization energy increases as you go up a group and increases as you move to the right. So the one that's higher up has the larger ionization energy, and that would be certainly lithium. So we'll mark that down, lithium. The next one is which one has a larger ionization energy? Element number 38, strontium, or element number 12, magnesium. And so let's pull out our periodic table again. We have strontium 38 or magnesium number 12. Okay, and so the ionization energy increases as you go up a group. So strontium is lower, magnesium is higher. So ionization energy for magnesium will be certainly higher than that of strontium. The next one here is sodium number 11 or aluminum number 13. Which one has the greater ionization energy? Okay, and we have sodium or aluminum. Okay, and sodium and aluminum are in the same period. That is the horizontal section of the periodic table. And as you move to the right, they get larger in ionization energy. So aluminum will have the larger ionization energy compared to sodium. The next one is going to be element number 55, and that is cesium, and element number 82, that is lead. So we have cesium and lead, that's cesium and lead. And which one has the greater ionization energy? They are in the same period. Lead is further to the right, so we'll have the greater ionization energy. Perfect. The next one here zoom in on that. I circled lead of the pair. The next one is either barium or fluorine, and which one has the larger ionization energy of barium or fluorine? So let's write that down. And so we've got our periodic table of barium, element 56, or fluorine, element number 9. And the one that is higher up and further to the right has the larger ionization energy. That would certainly be fluorine. So fluorine has the larger ionization energy. All right, so I want you to notice here for questions 12, 13, and 14 that we just completed, okay, of these questions, they are asking different questions. So the different question here is the larger electron affinity, larger electronegativity, larger ionization energy. You should note that electron affinity, electronegativity, and ionization energy all follow the same trend, and that's why the answers are all the same. Cool. That seems pretty simple, actually. All right, let's do another problem. All right, so our next problem here is number 15, and number 15 is going to be a little bit different. So I'm going to highlight this in different color. It's the larger radius, which is atomic size. And we are going to be dealing with the same elements that we just aforementioned, that we just talked about, but it is an opposite trend. So we're going to see an opposite pattern on this one. So we're going to go pull out our periodic table that deals with atomic size or radius of atoms. We are going to first compare sodium, that's element 11, and lithium, element 3. So let's plop on our periodic table for size. So we're comparing lithium and sodium, and which one has the greater size? The greater size is the one that's further down and further to the left. So sodium is larger than lithium. So let's zoom on here. So sodium is larger than lithium. Perfect. The next one that we have here is between strontium and magnesium, number 38 and number 12. So let's find those two elements on our periodic table. Number 38, strontium, and number 12, magnesium. Okay, in terms of size, atomic size, the one as you go down the group, they get larger. So strontium is going to be larger than magnesium. Strontium is larger than magnesium. Perfect. The next grouping here is going to be between sodium and aluminum in terms of size. So in terms of size, we have sodium or we have aluminum. So as you, since sodium and aluminum are in the same period, they decrease as moving to the right, but they increase as moving to the left. So sodium will be larger because it's further to the left. Sodium will be larger. The next one is between cesium and lead. That's element number 55 and 82. So 55 and 82, there's 55, there's 82. Okay, so as you move to the right within a period, they get smaller. So lead is smaller than cesium. Cesium is larger. So cesium is larger than lead. Perfect. We have one more of this grouping here to do. And that would be between barium, element number 56, and fluorine, element number 9. So let's find those on our periodic table. And that is barium number 56 or fluorine number 9. Which one is larger? Well, the size increases as you go down a group. Barium is further down, and the size decreases as you move to the right. And so therefore it increases in size as you move to the left. So barium is most certainly much larger than fluorine by far. Bingo, there we go. All right, so I made sure that I had 12, 13, 14, and 15 on the same page so that you can see the pattern here. That is, electron affinity, electronegativity, ionization energy are the same pattern and trend, and radius or atomic size are exactly opposite. All right, awesome. We do have some more questions to do here, and we have one more set of questions to do, and that is number 16. Which of each pair has a larger radius or atomic size? Calcium or ion or calcium metal. Okay. Oh, just a real quick selfless advertisement. I am the Crazy Hat Chemist. If you are learning chemistry, if you're enjoying watching these videos, or I'm not sure if it's an enjoyment process or not, but if you are learning something in chemistry here from these videos, then please like and subscribe. I would greatly appreciate that if that helps me out in some way or fashion. And I'm not really sure how that helps me out at this moment in time, but I'm sure it helps me out some way. All right. So here we go. Let's continue on. So we got calcium ion or calcium metal. And so what we need to do is we need to go back in time just a little bit and do the electron configuration of calcium. And so we're going to slap down a periodic table right here. And here is calcium. It is element number 20, as it states right here, element number 20. Okay. So element number 20, and we're going to write out the electron configuration for it. So just zooming out just a little bit, I'm going to go up and over. That's argon, so that's AR in brackets, and then it is a 4s2, 4s2. This would be for the calcium metal. So I'll zoom in on that there so you can see that. Then we have the calcium ion, calcium 2+ ion. So what has happened between calcium metal and calcium ion is it has a 2+ charge. Therefore, calcium metal will lose 2 electrons. Which 2 electrons? These 2 electrons. So it will have this 4s2 gone and disappeared. So if you have lost electrons, then that means if we were to draw these, this is a 4s. So if there's our nucleus, and then that's a 1s, that's a 2s, that's a 3s, and then a 4s. I'm going to compare that size compared to this ion. So this is the atom, and this is the ion. That's the nucleus, that's a 1s, that's a 2s, that's a 3s, and that is the 4s, right? So what has happened is that this 4s shell on the outside has lost 2 electrons and it's no longer there. What has happened to the size? It has become smaller. So the ion, a cation, they're positively charged, they're smaller than the atoms from which they come. So, which one is larger? The atom is larger, okay? All right, and then the next one is chloride, ion, or chlorine element, and we'll do that one here. Here is chlorine, it's up and over, so that is neon in brackets, and then that would be a 3s2 and a 3p5 for the atom. And then neon and a 3s2 and a 3p, oh my gosh, 6, because the ion has added 1 electron, right? So now what has happened is you've added 1 more electron to that outer shell, so then this one will be bigger and that one will be smaller. This one will be bigger because it's added 1 more electron, and that's on the outside. So you're just adding more on the outside. So what's bigger? Then this one is bigger. Okay, so you should see that cations are smaller than the atoms from which they come. Anions are larger than the atoms from which they come. All right. And then we're going to do one more here, and that one more is a copper that's a 1+ versus a copper that's a 2+. Well, we had just mentioned that if you have a cation, of which these are both, okay, they're both the same number of protons. If you lose 1 electron, then it gets smaller. If you lose 2 electrons, it gets even smaller still. So which one's larger? The 1+ ion of copper. If you want more detail as to why these are the case, then you most certainly need to be watching my honors chemistry video series on periodic trends. That would be very, very helpful to you. All right. But I believe that we have just answered all the questions on this worksheet. I'm going to put this entire worksheet up here so you can see the entirety of the whole thing. Okay, so this is our entire, let's see if we can get it all on one page here. It's quite large with many problems. Holy moly. Here we go. We are almost there. Yeah, I think we're actually finally making it here, folks. There we go. It's basic periodic trends worksheet, and I've done all the answers here. Notice that we did most certainly have to label our periodic table. We had to also have some trends for size, trends for ionization energy, trends for electronegativity, and trends for electron affinity, a whole bunch of trends. We also had trends with groups and families, and that is it. So I hope you have a fantastic day. You learn some chemistry, and I will see you next time. Cheerio until then. Bye for now.